Hello, I am Hyoung-Goo. Welcome to Financial Time Series class. You can Google my name like this, Hyung-Goo. Yeah, and then there is a first link. Okay, this is my website. So Hyung-Goo, this is my name, and then the first one is brief introduction about me. Let me click it. So yeah, you can know about me here. And next, the second link is important. By clicking second link, there is a list of classes I'm teaching. And then here it is, Financial Time Series Analysis. By clicking this one, you can access our class website or our cloud spaces so that there are all class materials are here. So basically, I will use this one. This is our textbook, Analysis of Financial Time Series, written by Louis Say. And then there lecture material. So let me click the first one. Okay. Tail lecture note and then free class reading. In the free class reading, there is a PDF file. Okay, so this is free class reading. Okay. So I can just briefly go over this one. Okay. Okay, so this is analysis of time series class or financial time series class. And then this one, this syllabus is written by Professor we say. He's very famous professor. And then this class originally designed for R, but in our class we will use Python instead, mostly Python. Okay, so let's move out. Okay, and then about lecture note, actually about lecture note, you can click this one by one. Say lecture note. I put important lecture note outside in the root folder, so you can simply click this one, the first one. Okay, so analysis of financial time series. Okay, so introduction. Okay, introduction. Financial time series FTS analysis is concerned with the theory and practice of asset valuation over time. And then we can skip this one. And objective of the course is to learn ways to get the financial information from web directly and to process information, to provide some basic knowledge of financial time series data such as skewness, heavy tails, measure of dependence between asset returns, to introduce some statistical tools, econometric model used for analyzing this series, and to gain experience in analyzing financial time series, and then to introduce risk development in financial econometrics and their application like high frequency financing, and to study methods for assessing market risk, credit risk, and expected loss. Okay, we can skip. So there are examples of financial time series like a daily log return of Apple stock or VIX index, okay, volatility index or CDS spread, credit default swap spread. If you want to know what is CDS spread, you can simply Google it or ask it to ChatGPT. By the way, in our class, we will use a lot of AI, generative AI model like ChatGPT or Cloud or quarterly earnings model, something like that. Okay, they are all time series model. U.S. monthly interest rate, exchange rate between U.S. dollar and euro, size of insurance claim, value of financial insurance claim, multiply with 1,000 krone that exceeded 500 from 1972 to 1999, 1992, or high frequency time series data, like tick by tick data of Caterpillar stock, something like that. This is typical daily log return of Apple stock, and then this is low density daily log return. Okay, daily log Apple stock. So basically, this movement is one observation, and then each movement we can generate like density histogram. First we generate histogram and then normalize it, then it becomes like a density. It becomes density like this. this CDS 3-year spread. Okay, let me slightly zoom out. Okay, and then this is the CBOE VIX index. Good. And then this is Coca-Cola earning per share. So there is clearly cycle here. And then dollar per euro. Okay. And then US EU. Okay. And something like that. And then log return. So we have a lot of data like this. Spread of monthly US interest rate. And then something like that. Okay, we can skip. So this is data. Yeah. So outline of the course, we can skip this part. Okay, let's go directly to the main topic, asset return. Let PT be the price of an asset at time t and assume no dividend. Then one period simple return is, gross return is 1 plus RT, which is PT over PT minus 1. Okay, simple ratio of price between two periods, it is gross return. Okay, or we can remove with PT is PT minus 1 plus RT. Simple return is minus 1. It is net return. Sometimes we call it net return. RT is ratio between the prices minus 1. So which is PT minus 1 over PT minus 1. Now, multi-period simple return, which is gross return. So return from PT minus K to PT. Okay. So it is a multi-period. So compounding, we compound it. So yeah, PT over PT minus 1, PT minus 1 over PT minus 2. So they cancels out. Then this one is obviously same to this one. And then we know each piece is this definition like this. So we plug this one over here. Okay. So K period return, K period multi-period simple return would be expressed like this one. Or K period simple return is RTK, which is PT T minus K minus 1. So example, table below gives 5 daily closing prices of Apple stock in December 2011. The 1 day gross return of the holding, the stock from 12.08 to 12.09, 1 plus RT, 393.62, which is basically 396 over 319.66, which is approximately 1.0076. So that the daily simple return is what? It is 0.76%. Okay, which is again this one minus 1, right? This one minus 1. So this is like this one. Okay, so from 8 to 9. Okay, it is a return between the 2 point. Now time interval is very important. Default is usually 1 year in finance. So in finance we usually annualize annual return a lot. So suppose 1 plus RTJ, J equal 0 to K minus 1. So K period return 1 over K. Okay, we divide 1 over K, power to 1 over K minus 1. It becomes annualized. Approximately, in log it is exact, but approximately this is approximately like this one, not same like this one. If we do the continuous compounding, so illustration of the power of the compounding, rate 10% per annum, so annual, okay, payment 1, 10%, so after 1 year, 10% return, it becomes like this one. Semi-annual return, okay, 10%, 10% semi-annual, so 5% for every 6 months. So we do this one, okay. So 5%, 5%, 2 times 5%, then we have this one. So if we do the infinite, we have something like this one, okay. So we know continuous compounding will be look like this one, okay. So A equals C. So this one is exactly matches this one, okay. So here R is 10%. Okay, R is 10%, and here it is 1, right? C starting value is 1, so we will have this one. So we can check it. So we can go to the Python. So collab research google.com slash hashtag create equals new. Okay, let's do this one. So here R is 10%. So R is 10%, 0.1. Okay, and then let's say N is here 1. Let's say N is 1. So here, and this is frequency. Okay, this is frequency. And then, well, uh, initial amount. Okay, C is, let's say it is 1. So it is initial amount. Then what? The A here, if we use the same notation, A would be, okay, A would be, okay, if we do a continuous compounding, then, okay, uh, 1 plus R, right? 1 plus R to the power of, so this is frequency, so we divide it by N, and to the power of N. In Python we do this one, and then let's print A. Okay, so, well, it is 1.1, obviously 1.1, right? It is the same, 1.1. Okay, how about we do the fine annual? Okay, if we do the 2 times, then, well, we will not divide by 2, divide 2, right? So we can keep N over here, and then this one, it is 1.0125. Okay, let me close this one. Yeah, exactly same. Let's say 4. Okay, 4. Okay, then it is 3 months. It is quarterly compounding. Yeah, we have this amount. Okay, this amount, quarterly compounding, same, right? Therefore, how about it is very large? N is like 400. Okay, 400, very large number. If it is like a very large number, then it becomes 1.105. So it would converge to this number, 517. But infinity, to the infinity, actually, we have, actually, is this one. If N is very large, it should be same to, uh, okay, NP and the R. Okay, R multi R. So it should be something like this. Also, yeah, import numpy SNP. Yeah, they are almost same. Okay, so I think you learned in high school. So N is very large. Okay, this number converges to exponential, right? Okay, exponential. So yeah, if it is infinity, something like this one. Okay, where R is interest rate per annum. Okay, annual. C is the initial capital, which we put it 1 over here, and is the number of years, and the exp is the exponential function. Okay, now present value, actually present value is in some sense inverse of this one, inverse of convergence. So, well, if we just continuously do that, then we C equal A exponential R n. So it is the present value of receiving A in n year later. Okay, n years later. So for example, R is 10%. So present value of present value of $100 receiving, if we continue the compounding, okay, R, and then 10 years later, okay, 10 years later, it would be the value is something like sorry, should NP. It about, it is less than half. Receiving $100 10 years later with discount rate, required rate of return 10% would be just $36, something like that. Okay. Now multi-period log return here, by the continuous compound log return would be something like this. RT is 1 over 1 plus RT, which is this one, which is the, because small p is log of big T, so well, in log, division is subtraction, so pt minus 1, because this is log big T, okay? Small p is log big P, okay? Now multi-period log return, okay? That's why we love log. In finance, this example shows why in finance we love log. So, well, k period return, okay? RTK, we take log 1 plus RTK. Again, 1 plus RTK, k period return is basically this one. Okay, this one. Okay. And then if we take log, okay, this one is decomposed into this one. Okay, k period return is compounding of a k period of unit period return, and it is log. In log, multiplication becomes addition. That's the beauty of log. So log 1 plus RT, we write a small r over here, something like that. So, well, it becomes addition. Okay. So what is the log return of, in case of log return of December 8 to December 9, okay? December 8 to December log return is here, where we have data. So we simply log and subtract between the two. Okay, something like this one. So log this one, and then 7.5%. What is log return from day? It is 7 day. Same. It is December 9th price, December 2nd price, and over 1%. Now portfolio return. Suppose, well, until now we see just return for one asset. How about portfolio return? Portfolio is a bundle of several assets. So that's the same. Portfolio return is basically weighted average of each one. Okay, so here W is weight, RIT is asset, I asset is in portfolio. So example, an investor holds stock of IBM, Microsoft, and Citigroup. 네. Assume that her capital allocate 30%, 30%, 40%. Use the monthly simple return of table 1.2 of the text. What is the mean simple return of her stock portfolio? Well, that should be simple. Okay, ERT would be 0.3, 1.35. Okay, so again, 30% weight and 2.62 and 40% 1.17. Okay, and then so we do have this one. Okay, so this is the answer. Okay, now dividend payment. By the way, table 1.2 is yeah, you can find the table 1.2 here. No, not here. Well, it should be somewhere over there. Okay, so we skip. It is because straightforward. And then what if there is a dividend? Well, when there is a dividend, there is another return. So when there is a dividend, RT would be PT plus DT because it is additional cash we receive, and divide PT minus 1, then return. Okay, if we take log, it's a log PT dt. PT 더하기 DT, PT plus DT is dividend. cum dividend price in some sense. So PT, DT, and PT minus 1. Now excess return. Now we have another important concept in finance, excess return. Adjusted for risk. It is return over benchmark. Okay, so here excess return ZT is RT minus R0T. Here R0T is benchmark return. Okay, reference set. Or in log, if you use log, this is actually more exact RT minus R0T. Okay, where R0T denotes the log return. Okay, of the reference set or benchmark asset. For example, like a risk-free interest rate. For equity fund manager, it is like benchmark would be like S&P 500 for Korea. It is Kospi 200. Now relationship RT equal log 1 plus RT. Then therefore R big RT is E small RT minus 1. If returns are in percentage, then RT would be 100 multiplied by log 1 plus R divided 100 if it is percent, right? So we can transform percent like this one, or this is in the same way like this one. Now temporal aggregation of return produces, okay, so it's a multi-period return. So k period we know this one, but again log is simpler, this one. Okay, by taking log, again this multiplication becomes summation. These two relations are important in practice is obtain annual return from monthly return. Okay, example. If the monthly log return of the asset are 4.46% minus 7.37% and 10.77%, then what is the corresponding quarterly log return? This is log return. Okay, so this is log return, so therefore we can simply add up. Okay, if monthly simple return, now we have simple return is 4.46% minus 7.36% like this, then what is the corresponding quarterly simple return? Then we have to compounding and then subtract 1, so we have this one. Now distributional property of the return. What is the distribution of this one? Okay, some theoretical properties. Okay, moments of random variable x with density fx, else moment is, this is in statistics it is important concept, and then this else multiplication of random variable x is expected value. It is called moment of the random variable. Moment is power, else power. Else moment is else power of random variable and takes expectation. Definition of expectation is the random variable and then multiply the density function and integrate from minus plus infinity. Then it is definition of mean. Okay, this is what you learn in high school. Now first mode, what if L is 1? It is we call it mean, expectation of a variable. Now L's central moment, if we subtract mean, where mu x mean, subtract mean and then power L, it is called central moment. If L is 2, it is second central moment. It has a special name which is called variance. Now skewness, and we have another important concept, skewness, symmetry, and kurtosis, fat tail. Okay, and then the definition of skewness, or which measures the extent of symmetry, is third central moment, and we normalize it with the third standard deviation. Standard deviation power of 3. Kurtosis is the measure of fat tail. Yes, something like this one. So if we subtract 3, from kurtosis, it is called excess kurtosis because the benchmark is 3. Okay, in normal distance, when they are symmetric, normal distance it is 3. Okay, so normally it is 3, so it is greater than 3, then the tail is thicker than normal distribution. It is less than 3, it is thinner than normal distribution. Now estimation. Okay, you can think about this question. Okay, now estimation. Suppose we have data from x1 to xt, time series data. Now sample mean. Okay, this is the random variable, functional random variable, so we can directly see this one from the data. Okay, it is a mathematical concept, so we cannot directly watch mean and variance in the data. All we can do is we can get sample mean and sample data. Okay, we have definition of sample mean. Okay, sample mean is this one, basically average. Now sample variance, which is squared. Okay, subtract data, subtract sample mean from the data and square it and get the average. When I get the average, we usually subtract -1. Okay, we sometimes we do not subtract -1. It doesn't matter. Okay, but when we subtract -1, it is called unbiased estimator. Okay, so here we subtract -1, but it is not necessary. Okay, you don't have to subtract -1 over here. Now sample skewness, again skewness here, this is the mathematical concept. Okay, so how we can estimate skewness out of data? Then this one. Okay, here we have this one and t-1. Again we have t-1, and then third central moment in sample mean. Okay, cutoff is something like that. Under normality assumption, the data is normal, then we know if data is normal, under normality assumption, this skewness follows this one, and cutoff is -3. This one follows normal distribution with mean 0 and variance is 24 divided by t. So this is under normality. So this is very important. This skew, this is important. This means that, okay, if we have a very large number of data which are drawn from normal distribution, and then we calculate this one, then it becomes very similar to this distribution. That's what it says. And again, suppose we sample many data. We sample many data from normal distribution and calculate this one and subtract 3 under normality. Okay, again, under normality means that we sample a lot of data from normal distribution. Then this kx -3 converges to the normal distribution with mean 0 and the variance 24 divided by t. T is the number of data, so we assume it is very large data, so t should be very large. Some simple test for normality for large n. Okay, so therefore in reverse, what we can say is that, okay, suppose if we have a very large large number of data, and then we calculate this one, and then this data, if it doesn't follow this normal distribution with mean 0 and 6/t, then what you can say that, okay, then we can say that this original data is not from normal distribution. Same, okay, only under the assumption of normal distribution this holds. So if we calculate this one and this estimation doesn't follow this distribution, or we observe very rare event of this one which is harder to explain from this normal distribution, then we can say that this data is not from normal distribution. So this is a basically idea. Okay, using this idea we can do, okay, test for normality, whether a data is from normal distribution or not. Okay, so test for symmetry. Remember, the sample skewness, given large number of data, the sample skewness follows normal 0, 6/t. So if we divide sample skewness with root of 6/t, something like this, this should follow normal distribution. Okay, so we calculate this one, and if it's a very rare event given this one, we can conclude that this data is not from normal distribution. Decision: reject null hypothesis. Null hypothesis is that the data is from normal distribution, and then we can reject null hypothesis on the symmetric distribution if this number is very extreme, too small or too large. Okay, usually we use a 5% rule or 1% rule. Okay, so if we calculate this number as star over here, and s star is, for example, like event which is likely to occur only 1% of a chance given this distribution, we can say that, well, because it is 1% event, very rare event. If the data is from normal distribution, this kind of 1% event is not likely to occur, and it occurred, therefore this data is not from normal distribution. That's basically decision rule. We can do test for tail thickness as well. Okay, so this sample kurtosis, we know sample kurtosis minus 3 follow distribution. So we subtract 3 and divide by root of 24 divided by t. Then this one should follow normal distribution if the data is from normal distribution. Okay, so the decision rule is the same. We calculate k star, and if it is too large, too small, usually rule of thumb is a plus minus 2. If it is greater than 2 or less than 2, we can say that, well, this is not likely to occur under normal distribution. It is a very rare event. This kind of rare event occurred, therefore the data is not likely to from normal distribution, therefore we reject the null hypothesis that the data is from normal distribution. Okay, so if we use this test for symmetry and test for tail thickness, then we can say, well, by this measure we can say whether the data is too the data is symmetric enough or not compared to normal distribution. If this is too asymmetric, we can reject the hypothesis for normal distribution. Again, test for tail thickness. If this is reject this one, tail is too thick or too thin, it is not likely from normal distribution. We reject. So we can use this test for symmetry and test for tail thickness to test whether data is normal distribution. Then why don't we simply combine those two? Then we have a very famous test for the Jacob-Error test. Okay. Well, under the normal distribution, we know S star is from N01, standard normal distribution, and K star is standard normal distribution, and then we square, if we square standard normal distribution as that, then we know the distribution becomes chi-square distribution, right? Okay, so we have two normal distribution here, and then we square them, add them. Then, well, we are adding squared to normal distribution. It becomes chi-square distribution with degree of freedom 2. Only when, of course, if normality hold. When x squared t denotes the chi-square distribution with 2 degree of freedom, okay, then the decision rule becomes decision H null hypothesis. We can reject the null hypothesis of no matter if JB is maybe too small, or actually too large, okay, because it's squared, okay, it's too large, or p value less than alpha, which means it's very unlikely to occur. Empirical property of reason. Okay, so demonstrate about data analysis. We can skip this one. Okay, R implementation. Okay, about this is R implementation, but we don't use R. Okay, we don't use R. So, and then instead we use Python. Okay, so, well, of course you can use R. R is a free open source program, so you can of course use R always. Okay, but in this class we use Python. Okay, so we can again go to our course website. Actually I closed it, so let me go to our course website again. So type Hyoung-Goo gang. Okay, this one, and then actually you can, of course, you can save this website. Okay, you can bookmark this website, of course, and then go to here. Okay, and the R demonstration. Okay, this is week 1, and we need this data. We need the S&P 500. No, we actually need this data. Okay, so here we can find this data. Okay, this lecture notes, and then this is week one, and then here, okay, here we find, we find, actually I can close this one. Okay, we find, okay, M monthly IBM 6708, maybe possibly from year 67 to '08 TXT. Okay, so this one, where is one? IBM. Okay, so actually this data, okay, M IBM 6708 data. So we need this data. Okay, so for Python, because we use Python, okay, here actually we can upload data. Okay, here Python. Okay, so here we upload this data. So you can download this data and upload this data. So actually this is my hard disk. So let me upload the data. I'm IBM 608. Okay. Okay. So I uploaded this data M IBM 6708. Okay. So well here, here. Okay. Now we want to read. Okay. DA. Okay. Okay. We can go. Okay. By the way, here actually, okay, let me delete this one. This is too, okay. We don't need this one. We don't need this one either. We can delete it. Actually, if we go to runtime here, and then we can runtime here, and then actually, instead of Python, we can use R. Okay. If we use R, okay, R and code, okay, and then paste. I can copy paste. Oh, I cannot. Well, let me copy and then paste over here. Huh. Okay. Okay. Yeah, I cannot copy. Okay. Okay. Then I can open the PDF file. In PDF file, I'm pretty sure you can copy and paste it. So in the PDF file, okay. So you can copy and paste that one. Okay. And then copy this one and paste it here. Okay. And then you can run it. Well, it works. So Google Colab, in Google Colab you can run Python. So okay, DA1, this one. So and then DA1 by this one. Yes, we have this one. Okay, same. Okay, so it is R. But here actually I want to use Python. Okay, so if you transform this on Python nowadays, of course, well, now I can change the runtime again. Runtime to the Python 3. Python 3. Okay, then this should not work because it's Python. Yeah, this is Python. It should not. So I can go to AI nowadays. Claude. This is Claude AI, Claude.ai. Okay, so transform the following R code to Python code and then paste. Here the equivalent. Okay, so equivalent Python code. Okay, so I can copy code and then I can go Python. Okay, let me delete this one again. Then import panda. Okay, it should be correct. Print. Okay, let's wait briefly. Okay, now it works. Okay, actually I don't need print over here. Here, okay, I can file. Okay, so well, you can generate data like this one. Okay, so yeah, it is R code. We can easily change the Python code with AI, and then we can do this one. Okay, okay, and then again go to Claude. Next, change this R to Python. Again, same. Oh, this is the code. Same. Okay, okay. Well, I don't know why it is so difficult to copy and paste. Okay, copy and paste. So okay. Instead, okay, I again go to my PDF. In fact, okay, what I can do is I can open with this one. Okay, just a moment. Yeah. Okay, let me copy and paste again here. Uh, okay, we wanna do this one. Okay, and then again transform from this R to Python. Let me do it again. Okay, now it works. Okay, so we can copy code and then we go here and then code again and then paste. Hmm. This is just a moment. Okay, there is a small code error. Okay, so I changed it. Again, I import panda, matplotlib library for picture, figures, and numpy. And then here in the previous line there was an error. Okay, instead of this one, the txt file. If we take a look at the txt file, okay, here this txt, this one, then it is the delimited white space. True. Okay, and the header is 0. So IBM is this one, and this one. Okay, and then yeah, then we take a log and then figure size and then we will plot return and then this is title x label y label create true, so this is time plot of monthly log return of IBM stock from this one. So we have IBM stock return like this. Okay, and then well, instead of this one, okay, here Okay, yeah, I do this one, and then we calculate mean, variance, skewness, and kurtosis. Okay, so we go here, RT. Okay, compute mean, variance, skewness, and kurtosis of R. Here, the data is what? This is RN, right? RT with Python. Okay, here RT. Okay, it is iterating this one. Okay, so well, I can just entirely copy and then here code and do this one. Okay, then it calculates mean of the log return like this, and we have a variance, so kurtosis. Okay, okay, so DA, if we put DA, the data header. Okay, the data is what? It is the monthly data, right? It is monthly data. So if we multiply 12 over here, okay, if we multiply 12, then it would be, of course, it will be annual return. So I have an annual return over 7%. Variance, of course, variance we can multiply 12. If we annualize, because it's monthly data, if we annualize, the variance is, of course, 6%. And skewness, well, those things we leave as it is, okay? Okay, and then, well, there is a basic stat RT, okay? Basic stat, okay? So in R, this is code for basic statistics, okay? So, but in Python, we have something similar, and then describe RT, okay? We describe RT, describe, okay? RT describe. Okay, it describe. Count, mean, standard deviation, and those things. Okay. If we wanna take a look at the only second one, of course, then we can do this one. Okay, one because Python starts from, yeah, 0. So second one is 1. So this is mean. Okay, something like this. So we can do the basic statistics. Now t-test. Okay, how about t-test? Test the mean log return is 0 or not. Okay, so how do t-test? Okay, okay, again I can go cloud. Okay, transform to Python. Okay, one sample t-test, then t-test, yeah, t-test looks like one sample t-test p-value. Okay, so well, we can only copy this relevant part over here. Okay, let me copy relevant part only. Perform one sample t-test, and then code. Perform one sample t-test. Well, t-stat piece, t-stat not defined, so I have to import this one. SciPy stats. Well, this ChatGPT or Claude, they are amazing. Nowadays it is very easy to learn code. Even though you know nothing about coding, Python, you can this advanced analysis like this. This is amazing. The one sample t-test, it is close to p-value is 5, slightly over 5%. Okay, 5. So the number would be very similar. Okay, t-test alternative true mean is equal to 0. So p-value is slightly over 5%. So 95% confidence interval is this one. So it is 0. Sample estimate is here, this one. So well, we cannot well, and so we cannot reject null hypothesis meaning 0 here, right? Because 0 is between this 95% interval. Even though here the mean is even though the mean is about 0.6%, statistically speaking, it is in the 95% confidence interval. Okay, it is range 95%, so it is 95% event, so we cannot reject null hypothesis. How about normative Jacobi test? Okay, normative Jacobi test. Okay, how about this one? Jacobi test. Well, so now these two Python Jacobi test. To perform Jacobi statistics, okay, then yeah, we need this one. Okay, and then code Jacobi, and then go to the cloud, and then JB stat and p value, perform Jacobi normality test. Okay, yeah, Jacobi normality test 3, JB statistics is this one, and the p value is very small. P value is at a Jacobi stat very high, so it means that we reject. Now we can reject null hypothesis here. Okay, we can reject null hypothesis. Okay, because it is very almost zero event. This kind of number, if the data, this IBM data is indeed from normal distribution, there is very unlikely to occur. Okay, with zero chance of occur, and this event actually occurred. Therefore, since under normality so rare event occurs, so therefore we cannot believe this is from normal distribution. So we reject null hypothesis that it is the normal distribution. Okay. Yeah. So here Jacobi, that is something like this. Well, we can do other thing. Okay. You can do similar thing with Python by combining ChatGPT and Python. So perform security tests like this one, and T stat. Okay, PV two normal, cover two side p value test statistics. Okay, and we have this one, and kurtosis divided by skewness about 24 divided 4. Okay, this one, and then Q. Okay, this is quit R. Okay, so well, instead of using this library, because we know formula for Jacobi statistics, so we can do one by one. Okay, we can calculate skewness and we can do kurtosis and then square them, of course, right? Here we have skewness, t-stat, t-stat p-value. On the p-value, we can get the t-stat, but it is, if we want to do two-sided test, it is both sides. Okay, so we have to multiply by 2. Okay, it is either plus 1.23 and minus 1 point smaller than minus 1.23. If we add it up, then it is like a 0.2. So it is like a 20% event in some sense. Okay, so it is like symmetric in some sense. We cannot reject the null hypothesis that it is. We cannot reject null hypothesis it is from normal distribution. Okay, but this one it is very large. It seems very large over here. Okay, now another important concept we will learn: normal and then log normal distribution. Suppose y is log normal. We call y is log normal distribution. If we take log of y and then that log y is normal distribution. Okay. So it is a bit confusing because y is indeed it is exponential normal distribution, right? But anyway, we call it log normal distribution because if we take log of this one, we have normal distribution. But in reality, log normal distribution is exponential of normal distribution. If x is normal distributed, mean is mu and variance is sigma squared, then y is exponential of x, exponential of normal distribution. Therefore, it is log normal distribution, and log normal with mean and variance or something like this. So it is a formula. Okay, by taking exponential of standard normal distribution with mean is mu and variance sigma squared, then this log normal distribution has mean of this one and variance of this one. Conversely, if y is log normal distribution, mean y mu y and variance sigma square y, then x normal with mean and variance this one. Okay, it is just transformation. Okay, application. Okay, if the log return of the asset is normally distribution with mean of 0.0119 and standard deviation 0.9063, then what is the mean and standard deviation with simple return? Okay, we can solve this problem in two steps based on the prior result. The mean and variance are where we know formula, so we can apply this formula. So simple return is this one. Therefore, we can substitute -1. So 0.014 is the mean and variance this one, and standard deviation 0.067. And then process concept, we can skip this one. Now likelihood function for self-study, but likelihood function is important, so we can briefly go over this likelihood function. Finally, it pays to study the likelihood function of return. Okay, R1, RT. Discussed in the chapter 1. The basic concept is joint distribution, a conditional distribution, and marginal distribution. Okay, joint distribution is basically the definition of a joint distribution is conditional distribution, marginal distribution, and something like this one. Okay. For two consecutive return R1 and R2, if R1, the joint density of R1 and R2 occurring is of course density. Okay. Conditional distribution R1 occurring, and given that R1 occurs, then R2 occurs, right? That's the joint distribution. What if we have three returns, three observation, R1, R2, R3? Then we can just say the conditional on observing R1 and R2. We can describe the distribution R3 like this one. Of course, R2, R1 like this one. In general, therefore, if we have this one, we can decompose into this one and this way, and then yeah, like this one. Here, this is a product. Okay, multiplication from T2 to big T. If RT minus R is normal with mean mu T and variance sigma square, then likelihood function becomes, okay, then the likelihood function of this one, and then this should be look like this one. Okay, for simplicity, if FR1 is ignored, if you ignore this one, because simply this is constant, we observe R1, this is constant, then the likelihood function becomes, okay, from, in some sense, probability or probability density of observing from R1 to RT is product of this one. This is called conditional likelihood function of return under normality. Well, it is only normality. If it is not normal distribution, then we have different functional form. Okay, not exponential and 2 pi sigma thing. Okay. Now, model specification. Okay, quantifying dependency. Now, correlation coefficient. Okay, consider two variable and x, y. Consider correlation such that rho is covariance xy and standard deviation xy. Okay, this definition correlation. And then you have Kendall's tau. Okay, what is Kendall's tau? Kendall's tau is another important concept. It is similar to correlation, but actually it's more robust in some sense. Let x, y be a random copy of x, y. Then candles tau, load tau is px minus x tilde y tilde, which is greater than 0 minus 0. Okay? So in instance, it is sine of x minus x tilde minus y tilde. This measure quantities the probability concordant over discordant. Okay? Concordant means they are both plus, like both minus. Okay? Discordant means 1 plus 1 minus. Here, concordance here means that y tilde x tilde y tilde is greater than 0. So both positive or both negative. For spherical distribution, normal. Okay, this is the for spherical distribution, like normal distribution. The Candel's tau is there is an analytic solution for Candel's tau. Candel's tau is 2 over pi sine inverse of law. And then here's another important concept called Spearman's law. Is rank correlation. Let fxx and fyy be the cumulative distribution function of x and y. Okay? In some sense, they are the rank. This is rank of x and rank of normalized. Okay? Normalized such that from 0 to 1. Rank is normalized from 0 to 1. Okay? Then once we ranking the random data and then we calculate correlation between based on those ranking, then we have Spearman's law. That is the correlation coefficient, the probability transformed variable. It is just the correlation coefficient, the rank of the data. So based on rank. So it is more robust to extreme outliers. So why do we consider different measure of dependence? Correlation coefficient encounters problem when distributions are non-normal. This is particularly relevant in risk management. Correlation coefficient focus no linear dependence. It is not robust outlier. Okay, the actual range of correlation coefficient can be much smaller than -1 to 1. Next, we have another R demonstration. Again, you can transform. Of course, you can transform this into Python. Okay, but here I won't do it. Okay, so well, this is the way to calculate correlation, and then yeah, correlation between S&P, IBM. Yeah, that's like that. Okay, actually we can try this one. Okay, copy this one. Okay, so here, okay, so we can only copy this two line here, and then code we can, okay, this one, yeah, so IBM and then S&P 100. Okay, and then what else? We can calculate correlation. I think in Python I can do the, okay, now, okay, correlation into Python, to Python. This is very kind. Okay, so correlation, okay, here, so we can get correlation like this. Okay, correlation and IBM and S&P return is like 0.56. Actually, I think I can do this one. Let me check. Huh. NP, I'm not sure. Well, this doesn't work. Okay, let's go back to the previous one. This is the correct one. So this is correlation. Okay, something like this. Okay, so correlation. Let me check the answer. This is the looks exactly same. Okay, exactly same. And then how about candle correlation? To Python, we can exploit AI candle length correlation. Okay, so we need library here. Copy, make copy code, and then go this one, and then code here. Okay, I don't need this one, and then we don't need this one. Okay, calculate candle length coefficient between SMP IBM. Okay, so candle length correlation between SMP return and IBM is correlation is 0.42. P value is very small, so there is a correlation. Okay, there is a positive correlation, strong positive correlation. Okay, in terms of candle length correlation between IBM and S&P 100. So when S&P goes up, IBM is likely go up. When S&P go down, IBM is likely go down as well. Something like that. How does Spearman? Okay, there is Spearman. Okay, now it is fine-tuned. So let me just copy this one. Spearman correlation. Again, copy, and then code. Then I can delete this line, and then Spearman correlation. Yes, Spearman correlation. Again, there is a strong correlation. Okay, significantly, yeah, very rare in a very small number, which means that it is significant in terms of the Spearman rank correlation. There is a very strong positive correlation. Okay, actually we can do it, and we can do it analytically because we know formula. We can get the rank, and a correlation. Well, it is Spearman correlation. Well, this one, which is should be have the same number as this one, and the x1 times this one times, yeah, looks like this one, and then you can get z norm and the exponential of this one 20 correlation xy. Well, then its correlation is basically in terms of candle correlation, speculate is what. This is very interesting. Okay, here, this is a random number. The transformation of random number. Okay, x is simply exponential of z, but then y is a 20 of this one. So if we calculate correlation of y and x, it is basically driven by same z. But correlation is very low over here, although both x and y is basically from same z. Okay, so in that sense, correlation is not a good measure. But if we calculate candle measure and spear measure, we basically it's basically based on rank and core movement. They generate correct answer one, strong positive correlation between, even though, yeah, between these two numbers, because they are basically from same underlying process Z. So we have takeaways, and then R command used to produce plus in lecture one. Okay, and again I will not do this one because now it is the straightforward how to transform this R code to Python. Okay. Next, linear time series model. Linear time series model. Linear time series model. Finite time series collection of financial measure over time. Here's for example log return. Again, data is the t data point. Purpose is what is the information contained R. Okay. Now that's by observing this data, t data point, we want to know information contained in RT. So basic concept here, as for the stationarity, there's a two type of stationarity: strict stationarity and weak stationarity. Strict stationarity means the distribute are time invariant, where number is different, but the entire data is from the same distribution. Weak stationarity, the first two moments, what was first two moments? X and x square, mean of x and mean of x square. Okay, so 이렇게 mean and variance. As far as they are time invariant, they are weak stationarity. So what does weak stationarity mean in practice? Mean in practice that the mean and variance that it is time invariant. It is they are from the same distribution, the same mean and variance. So past time plus RT varies around the fixed level within the finite range, and future the first two moments of future RT are the same as those of data, so that meaningful inference can be made. That's why stationarity is important. If underlying distribution change, we can learn from anything from the past, right? As far as data is stationary and they are from the same distribution, but then by collecting the data, we can learn the distribution. We can learn the distribution from the history as far as the process stationary. Therefore, stationarity is very important. And the mean of return like this one, variance or variance of return or variability of return is defined like this one. Again, sample mean or sample variance are used to estimate like this. And now test. Test of 0, okay? Mean is 0 or not. Then what we do is we calculate t-value. T-value are which is the sample mean divided sample standard deviation. Sample standard deviation, okay? Sample standard deviation, this one. And then compare this t ratio with normal distribution. Decision rule is that reject null hypothesis of 0 if t is greater than this one or p-value less than alpha. Now lag t autocorrelation. Okay, what is the weather history affect today's return? K period before event affects today's return, something like that. Okay, so it's the lag K auto covariance. It's covariance, but covariance with itself. So that's why we have auto. This auto covariance. Now serial correlation. Okay, we have covariance, so which means that we can calculate correlation. So serial or auto correlation is this one. Note that low 0 is 1 and low k is low k minus k, because we can change the order for k equals 0. Why? Well, you can check it. Where low 0 means that they are the same, right? The denominator is the same, and k minus k, well, if you plug k over here, you can basically get the same number. So existence of serial correlation implies that the return is predictable, indicating market inefficiency. If it is stock return, meaning it means that, well, k period before return affects today's return. They are correlated. It means that history affects today's return. Okay, which is market is possibly inefficient because we can predict stock return with simply historical data. Now sample autocorrelation function, ACF, sample autocorrelation function, is the sample analog of this concept. Okay, sample analog of this autocovariance, self-serial correlation is sample analog of this one. So what is the sample analog of this? Of course, we can cross and variance. Okay, then we have a sample analog of the correlation, where R bar is the sample mean and T is the sample size. Now we can test the zero serial correlation, which is market inefficient or not. Individual test, for example, is that we can, well, R0 is 1, R0, R1 is 0 or not. Okay, there is a serial correlation with history. Okay, decision rule is reject. It's not if this is greater than some threshold number or less than threshold number. Okay, now joint test, which is called Lung box statistic, it means that H naught is all the correlation is zero basically. This is the formula. Okay, this is the sample statistics. So null hypothesis, null hypothesis, this one. Okay, this L is from 1 to K. Okay, we collect M period data, M correlation, and check that they are all zero, jointly all zero. Okay, and then sample statistic this one. If this is too large or too small, we can reject this null hypothesis. Asymmetry calculate this with M degree of freedom. Okay, decision rule reject H naught. This is greater than or p value less than alpha. It is chi-square distribution, so we check whether it is greater than threshold values. Okay, well, if market is efficient, they should be all zero. History should not be useful to predict the future, but because of sometimes data issue, there is possibly serial correlation like a non-synchronous trading, or which we will explain chapter 5, or bid-ask bounds or risk premium. Thus, significant sample autocorrelation function does not necessarily imply market inefficiency. They are simply possibly technical issue like this one. Okay, example, monthly return IBM stock from 1926 to 1997. Okay, so Q5. Okay, Q5. What is Q5? M is 5. So, well, it's monthly return. So it is like 1 month correlation, 2 months correlation, and the 5 months correlation to the 5 months correlation. They are all zero or not. Okay, and then sample statistics like this on 5 is this on 10 is it becomes larger and larger. If with RT log return, we have this one. So what is p value? How to use it? And implication is that, well, this is a large number, so monthly IBM stock return do not have a significant serial correlation because this is too small. This number is too small. Okay. And then in case of crisp valuated index, then this is surprisingly large or highly significant. This is very large number. Okay, this is very small number 5, and but this is very large number to significant. The implication there is a significant serial correlation in the valuated index return. This is possible non-synchronous trading might explain existence of serial correlation among other regions. Okay, so even though there is an individual stock level, there is no serial correlation. But at the portfolio level, there is possibly correlation. That does not make sense, right? If individually there is no serial correlation, autocorrelation, their portfolio is a collection of those individual ones, so there shouldn't be any autocorrelation. But because trading is a non-synchronous, they are all not all simultaneous occur, non-synchronous. Therefore, there's a possibility. There is a possibility of correlation, but that does not mean it's market inefficient. It is just possible data issue. It doesn't matter we can make money because it's just a data issue. Where are demonstration? Okay, again same data and autocorrelation function. Okay, well, actually, yeah, we can check this one. To calculate autocorrelation function of the IBM column plot ACF, then, well, we can copy code and then code like this. Well, we don't need to line, and then we don't need this one. We don't need this one. Okay. Plot the autocorrelation function. Yeah, autocorrelation function. They are all autocorrelation. Well, the first one is itself, so it should be one, but other autocorrelation is all very close. This blue one is range. Okay, they significant range, but they are all below that. So in IBM, there is autocorrelation is very close to zero. Okay, so autocorrelation function looks like this. One. Well, obtain the partial autocorrelation function. Partial autocorrelation. Copy, and then code, delete this one, delete this one. Okay, well, it becomes slow and slow. Okay, well, it can generate the value for partial autocorrelation function. Okay, of course, to remind you, you can always ask what is the difference between the ACF and PACF autocorrelation function, partial autocorrelation function. The autocorrelation function and the partial autocorrelation function are both used to analyze the correlation structure in time series, but they provide different information about the relation between observations at different lengths. Autocorrelation function measure correlation between time series and its lagged value. Your partial autocorrelation function measures the correlation between the time series and its lagged value, while context for the correlation at short lag. Okay, something like that. So key difference. The A-shape considers both direct and indirect correlation, while partial autocorrelation focuses on difference, direct correlation after removing the influence shorter lag. Okay. And then A-shape is useful to identify overall serial correlation in detecting seasonal or periodic pattern, while the partial autocorrelation function is useful for identifying the specific lag. Okay. At which the time series is directly related to the past value. And the A-shape, well, this is perfect explanation. Okay. Sometimes this AI generates wrong information, but at least this information is correct. The ACF helps in identifying the presence and strength of autocorrelation, while the PACF helps in determining the order of the auto or regressive model. Okay, because we know exactly where the correlation happens. Okay, so this is a box text like 10. Okay, box pierce test, and then backshift operator. Okay, actually we can do this one. To perform box pierce test for serial correlation, then we have copy code, huh, test BP test. Okay, so there's an error. So instead of this one, well, I can simply let's see BP test. Okay, okay, we just the PP test result. Okay, p-value and everything. So p-value is pretty large, so we cannot reject null hypothesis over here. Right, something like that. And then we have back shift leg operator. A useful notation in time series generation is definitely BRT. If we put B, it is a back operator. So if you put RT minus LT or LT minus LRT is RT minus 1. So move time. Okay. How about B square? B square RT is BBRT. So if you put RT minus 2. B or L, backshift or leg operator. Usually I use leg operator L, but here use B. Okay. Anyway, B means the shift. BRT is the value of city at time t minus 1. Suppose the daily log return is like this, then to answer the following question: what is RT? R2, BR3. If you could R4, it should become R 3, actually 3 minus 3 because R2, 2, so they all should be generally the same answer, right? A proper process of time data point, available data. It is the return is decomposed in two parts, like a proper perspective at time point t. Suppose we have available data f1, f2, or t minus 1. Okay, so it is about history up to t minus 1. We can denote the history up to t minus 1 as ft minus 1. Now the return is decomposed into two parts, rt, predictable part, and not predictable part. Well, predictable part means the predictable with respect to our history. History is ft minus 1 plus something not predictable. Therefore, in other words, given the information ft minus 1, okay, which is the history of r up to t minus 1, then rt is mu t plus at, which is rt conditional on conditional expectation ft minus 1, and then sigma t epsilon t is the variance, where t is a conditional mean of rt mu, a is a shock or innovation at time t, epsilon is I is equal to mean 0 and variance 1. Okay, so it is like a normalized. It is conditional standard deviation, commonly called volatility in finance. Okay, so this one is this one. Epsilon t is from standard normal distribution. Okay, traditional time series modeling is concerned with mu. Modeling for mu is mean equation. Now volatility, we can also do volatility modeling for sigma t here. Model for sigma t is a volatility equation. So univariate time series analysis serves two purposes: a model for mu t, and then understanding model for volatility t, property of forecasting, etc. Actually, I can a bit lower this one, make it smaller. Actually, yes, okay, this is better. So linear time series model. Linear time series model. RT is linear if we have this one.